Hello and welcome to Precision Stuff. Today we'll be continuing to discuss battery electrical modeling and look at some more graphical methods to learn about current, power, energy, and how you can't get what you want. And then we'll follow up with additional dynamic models of the battery. So previously we looked at a very simple model, which was a voltage source and a fixed resistor. And that was our battery model, and we derived a lot of valuable properties. And then we looked at the voltage versus SOC curve, and we looked at that for both the open circuit voltage as well as the load voltage. And we're going to develop this a little bit further. So one of the big questions you might have is, well, this is my voltage as a function of current, but how much current can I get out of it? And how much power can I get out of it? And how does that impact things? So let's see, let's draw the open circuit voltage for a cell. We can get really good at drawing this shape. We have our Vmin, we have our Vmax. And let's say that we're operating right here in the middle, and we want to do a very aggressive discharge, but we want to respect the voltage minimum of the cell. And for units, we have voltage, we have amp hours removed, which is my way of describing SOC, from 0 to max. And this is Vmin. This is Vmax of the cell, operating limits. We start here at middle SOC, we discharge, we get a voltage drop. So I'm drawing a huge amount of current. What current can I draw that gets me to Vmin? Well, let's calculate that. I discharge equals V of SOC, where you are, minus Vmin divided by R discharge of SOC. So depending on where you are in the curve, you can pull this much current before you hit the voltage rail. Likewise, if we wanted to charge at maximum capability upwards, we'd have a similar situation. The current charge is, in this case, Vmax minus V of SOC divided by R charge of SOC. And I'm doing R charge and R discharge because technically they are different in both directions, and with enough data you can figure that out. So a few things, it becomes pretty clear that at low states of charge you cannot discharge very hard. That's pretty obvious. But what about the power? The power discharge is simply I discharge times the load voltage, which in this case, if I'm drawing down to Vmin, is times Vmin. And likewise for power charge, it's the charge current times Vmax. Note that power charge is probably higher than power discharge because Vmax is bigger than Vmin, depending on where you are in the SOC curve. Let's actually plot all this out though, because it's going to be pretty important. Let's call positive I discharge, negative I charge. This curve, let's assume that resistance is pretty flat, which truthfully it's not, but let's give that an assumption. It's just an offset of the SOC curve. So let's draw this. So the discharge plot looks something like this as a function of SOC. And then the charge plot is also just an offset of the SOC curve. It's a little bit different, but it looks something like this. So these are the discharge and charge capabilities. Understandably, at low SOC, your discharge capability goes down and your charge capability goes up, and the reverse is true at top of charge. And now let's say that your resistance skyrockets at low SOC, which is pretty common. Then that means that this current would kind of drop down a little bit lower than that, and this current as well would have some sort of taper off here. That's like more realistic. I think everyone knows that you can't get a lot of power at low states of charge, but the opposite is true at high states of charge. You actually can't get a lot of charge power when you're mostly charged, which is pretty obvious. This is a problem if you're doing regen in a vehicle. Let's say you have a fully charged electric vehicle, you're going on some long road trip, and you slowly drive down the street, and then you brake aggressively using regenerative braking. The regenerative brakes won't be there because you are like right here on the SOC curve, and your charge current capability is really, really low, and all of a sudden the motor cannot produce the braking torque without overvolting the battery. This is actually a pretty real problem. Let's say you have an electric skateboard and you live on the top of a hill and you fully charge your electric skateboard and you're going down said hill. Your battery is full, the motor will not put more amps into it, you will not have regenerative braking, and you might have a bad day. So this can be a problem in vehicles sometimes. Okay, what about power? Well, we know that the power is just a multiple of the current. So let's scale this up. And let's take I discharge and multiply it by Vmin, 2.5. I'm just gonna, kind of roughly scale that. And then likewise, the charge power is just times V max. So I'm going to scale that as well. You get these nice swoopy curves. And essentially, this determines what you can do. So if you want to do aggressive discharge, you got to be at high SOC. If you want to do aggressive charge, you got to be at low SOC, although that can be damaging for other reasons. So this is power charge, this is I charge, and this is power discharge, I discharge. And we'll revisit this in a second. So how does this impact energy? Well, let's say that you are, say you're going to do a constant power discharge, and you're going to respect the voltage limits of the cell for lifetime and safety and regulatory reasons, etc. And let's say you do a slight low power constant power discharge, and your resistance curve is pretty flat. So you have a small voltage drop, and you're below the curve, you're below the curve, you're below the curve. Your current is going up as your voltage is going down, so technically it should start dropping faster. Okay. Now let's do an even more aggressive constant power discharge. And you have a higher voltage drop, and you're drawing more current, and then this voltage drops even faster. Well, what's going on here? Well, that means that as you increase the power, as power, goes up, your available amp hours goes down because you have to stop the party right here. So again, we have voltage, we have amp hours, and the difference between the low power discharge and the high power discharge is that you can get fewer amp hours out of the battery before you stop. Well, why does this matter? Well, area under this curve is, of course, energy delivered to the load. That's what we want. And the area between OCV and the load voltage is, of course, dissipation. That's what we pay for thermally. It's not great, but we know how to handle it. What is this area? Well, this is the energy that's in the cell that we just couldn't get. It's inaccessible. So we lost voltage in our voltage drop because of high current. And then we also lost amp hours because we were discharging at a high power and we hit the voltage limit early. And this is basically energy that is inaccessible. And this is actually a huge problem. If you want to run at high power, you could easily lose 25% of your available energy. And that means you might buy 100 kilowatt hours of battery, and you deliver 75 kilowatt hours to the load, and maybe like 5 or 10 gets burned up, and the rest is just not accessible. And this can be a huge issue for sizing vehicles. And it's not only an issue for constant power discharges. So if we wanted to summarize this experience, it would look something like, energy delivered versus power. And you'd get a, if you have E max, this is you slowly discharge, and you get pretty close to maximum while your power is low, and then all of a sudden it falls off a cliff. And technically, if you draw a high enough power, you can immediately collapse the voltage from Vmax to Vmin. And that would be at beginning of charge, you would really just like slam it all the way down from 4.2 to 2.5. That's pretty unusual, but there is a trade-off curve here, and you might find yourself operating at high power and losing a lot of energy. Okay, back to pulse loads. Let's say you are driving a race car around a track, and your power versus time looks something like, long straightaway, going around corners and stuff, long straightaway, going around corners and stuff, and it happens every single lap. So you have this regular pulse. What does that do to your available energy? Well, draw the same curve, voltage versus amp hours, and what we're going to find is that our load voltage has a drop, it recovers, we're below the curve because we're drawing some current, it drops again, and we keep going down, then it drops again. It gets really dicey here, but we're still fine. And then all of a sudden in that fourth lap, boom, we have crossed the minimum voltage threshold. We drew too much power than what the cell could actually handle, and we had to stop the party early. So this may be a problem in your application, and what you could do is either limit your peak power everywhere, but you're going slow on lap 1 and lap 2, or you could say, I'm just going to, reduce my power as a function of SOC because I know in my lookup table here, at this SOC, what is my discharge power that's actually available? Another common application is EVTOLs. If you want to have a hovering, flying electric object, its power profile looks something like this. You have a huge hover power, then you transition to cruise, and you move a long distance, and you do useful things, and then you hover again to land. Now the problem is, you lose this is a really high power pulse that occurs at low SOC, and that power pulse has to fit underneath this power curve. And even though you have tons of energy left over that you would love to use in your cruise phase down here, you actually have to limit the range of your vehicle based off of the ability to support peak power at low SOC so you can land, because landing is pretty important. So the energy available as a function of discharge power drops off rapidly, and if you have a pulsed application, you're going to suffer from the same results, even if your average power is pretty low. This is all still like modeling of energy and current and power with this really simple system, and it doesn't do a good job of predicting dynamic systems, like whether if your current and power are varying strongly with time, and we'll get to that right now. So let's do a little experiment. So we take our lovely model, which is easy but wrong, as all models are, and then we do an experiment, which is we run a 1 amp pulse for 1 second. So this is time, and then this here is going to be current, and we want to look at the voltage. How does the load voltage respond? Well, it starts at some voltage, and then the moment the current shows up, we get a voltage drop, and that is simply I times R, and then it's basically flat, and then it will recover when the voltage disappears. Now technically this is a tiny slope to it, because when you're drawing 1 amp for 1 second, you're traversing a small amount of the SOC curve, and the voltage should sag a little bit just because of how the voltage changes with SOC. But we're going to eliminate that by focusing on a really short time scale. So this is what our model predicts. The problem is when you run this experiment, you get a very different result in reality. Here's what you actually see. You see a instantaneous drop, and then it keeps going, and then it recovers instantaneously a little bit, and then that recovery continues. And this is really spooky, because our model can't explain it. Our model is not time dependent. It's just, you give me a current, I tell you the voltage. So we need a little bit more model capability to explore this. And from a physics standpoint, the cell has capacitance, the cell has diffusion, the cell has real physics that occur that are time dependent, and our model does not, so we should improve our model functionality. So we need to add dynamics to the model. So the way people typically do this is they make a 2 RC pair model. So we keep our same voltage as a function of SOC. We have our same resistor, we call it R0 now, and then we add in an RC pair. So this is R1, C1, and then actually we're going to throw in another RC pair for funsies. R2, C2, and technically you could keep on adding more. Like, this is a model, the goal is to predict reality even if you can't understand reality. So you could put 3 or 4 or 5 terms, you're probably going to get diminishing returns, it's harder to measure, you might not need it. 2 RCs is usually good enough. So here is our new battery model, and the output voltage now has impact from these 3 parts, 2 of which are actually dynamic. So how do we actually understand the response of this system? So if you take a RC parallel system, and let's say you put a current step into it. We're going to do a step in current. How does the system respond in time? Well, eventually, over long periods of time, time t equals infinity, the output voltage should just be I times R. And that's because eventually the capacitor is filled, all the dynamics disappear, no voltages are changing, and all the current has to go through the resistor, it can't go through the capacitor anymore. In the very first moment in time, the capacitor is not charged, there is 0 volts across the resistor, and all the current will go through the capacitor and it will start to charge up. And this is it'll charge up as I over C, and you get this classic exponential kind of capacitor charging curve. So V of time equals V infinity times 1 minus e to the t over tau. And in this case, V infinity equals I times R, and tau equals R times C. This is very similar to the capacitor charging situation, but we're just putting in a current step instead of a voltage step. Cool. We can actually solve this. If you put a current step into a battery system, that current step shows up everywhere. All these systems are in series. The current through this whole chain has to be the same. So you can actually treat all these independently. Like the R0 will respond instantly to the current, and this term will have a tau 1, which will respond on some time constant, and this term will have a tau 2, which will respond on a different time constant, and you can just add all the terms together, and all of a sudden you can now predict this dynamic behavior. Let's say T1 is on the order of 1 to 5 seconds, and then T2 is on the order of 10 to 50. This is like reasonable for battery cells. Of course, your cell will vary, and you can probably guess at what these time constants are just by looking at the voltage plot. I'm going to just, for the sake of math, use 1 and 10. They're round numbers, they're an order of magnitude apart. That's going to help us in a second. But remember, you can choose as many of these RC pairs as you want and fit them as long as it does a good job predicting your voltage response. So let's do this experiment. And let's say at time 0 plus, which is right after the spike, we are going to measure voltage. We're also going to measure voltage at 1 second and at 10 seconds. I've now squeezed the time around, don't worry. V battery is going to be, V of OCV, and then it's going to be minus R0 I, and this is at time t equals 0. Nothing else has responded. That's it. And so if we just want to look at the drops, you can say, okay, the voltage drop is this term. So V drop equals R0 times I. Now let's look at 1 second. So V drop of 1 second in. Well, we have the R0 times I component, and now we have to incorporate these two. So we're going to have V infinity, so we're going to have a plus I R1 times 1 minus e to the 1 second over 1 second, because it's tau 1. And then we're going to have a plus I R2, 1 minus e, this is going to be 1 second over 10 seconds. So how do we actually work with this? Well, we already did the first experiment. Our first data point tells us instantaneously how much the voltage drops. We know the current, so we can solve for R0. R0 is known, so this term is already known. And then we say, well, we know what this term is. This is to the minus 1. E to the minus 1 is 1 over e. 1 minus that is about 0.632. And then, because that is like 1 time constant in exactly. Now, being 1/10 of a time constant in means almost nothing has happened. So, the second term is basically not responding yet, and technically the answer is 0.095. So we get this, we get all of I times R0, we get most of I times R1, and we get just a little bit of I times R2. And if we look at V drop of 10 seconds, this thing continues to evolve. Again, we get R0 times I. Now we get plus I R1, 1 minus negative 10 over 1. When you're 10 time constants in, you're way out here near fully charged. Technically, this value is 0.99995, but we're basically going to call this 1. And now we're 1 time constant in to T2. So plus I times R2, 1 minus e to the minus 10 over 10, and that value is 0.632. So even if you just had an Arduino and a resistor, or an oscilloscope and a constant current load, and you did this pulse, and you basically did a pulse in current or a step in current, you could actually figure out, if you guessed at the taus, you know the equations, you can pick a few interesting points, and you can solve for what the r's are, and you get a matrix something like 1, 0, 0, 1, 0.63, 0.095, 1, 1, 0.63 times, R0, R1, R2. I'll throw the I up front, equals V of 0, V of 1 second, V of 10 seconds. And so just by picking a few points, and by knowing the exponential response of the system, and it helps that these two time constants are probably an order of magnitude apart, you can now solve for R0, R1, and R2. And this is like the really quick and simple way of just picking a few points. Technically, you could do an entire curve fit if you wanted to throw a little bit more compute at it. And as you get more and more data sets, you can get higher confidence in R0, R1, R2. And then we say, well, we know what tau 1 is. Tau 1 is R1 times C1. We just measured what R is empirically by looking at the voltage curve. Now we know what C1 is. So you can do some quick experiments, some current pulses to figure out all your R's, all your C's. You can build a more complex dynamic model. And now that you have a better ability to predict the cell voltage as a function of current, now you can predict, if you give a power, you now predict the voltage, you can predict the current, you can now predict the heating, because there's going to be heating in all of these elements. And now we have a much more capable dynamic model of the cell. And if you're doing rapid discharges or rapid charges, this is going to be much more faithful at predicting voltages, energies, currents, and powers than our simple system here. In terms of how these components vary, all your R's are going to vary with charge versus discharge. In general, charge resistances are higher. They're going to vary with SOC. In general, they go up at low SOC and maybe also up at high SOC. They're also going to vary with temperature. So this becomes a kind of experimental and data science problem of, I need to take this cell, I need to put it at different temperatures, I need to put it at different states of charge, I need to run a bunch of steps through it and figure out all these properties. And you make a huge lookup table, and the lookup table feeds into your dynamic model, and all of a sudden you can make really accurate predictions of what your battery will do electrically, and therefore you can get accurate predictions of what it's going to do thermally as well. This takes a lot of work. You might have a full-time team running electrical test, cell characterization, but if you're a small team, small company, you can do some really simple work with an oscilloscope and a load, or an Arduino and a resistor, and you can figure out what some of these parameters are and get a better idea of how your system will behave. Thank you for listening to Precision Stuff as we continue further in our battery journey together.